So last thing we're going to look at is section 5.5. So we'll look at a little bit of graphing, and then we'll also look at a word problem involving logarithms. All right, so there's only two bases that the calculator can do by pressing a single button. Can someone remind me again? I know we've done it a couple times, but what are the two bases? Yeah?
Base 10 and base 8.
Base 10 and base e. So what if I wanted you to figure out something like this? What's the log of 5, but I'm using base 3 instead of base 10 or base e? Well, there's a formula to be able to do that. Okay. Yeah, question, Sam?
Oh no, I was just gonna. Oh, I thought you were asking a question on how to do that.
So I'll show you what the formula is, and then we can try doing an example. So if you have log base b of x, there's actually two ways you can type this in. It does not matter which way you do it. The first way is using the common log button. And all you have to do is take the common log of the argument and divide by the common log of what's in the base. And that's it. So like, if I was going to try to type this into the calculator, I would type it in like this. Log 5, so log 5 divided by log 3. Just make sure you close your parenthesis on that first one or it'll mess up. Log 5 divided by log 3, and that's the answer. 1.46. Okay. The other way to type it in is using the ln button. So you can take the ln of the argument and divide by the ln of the base, and you'll get exactly the same thing. ln 5 divided by ln 3, hit enter, and I still get 1.46. So that's how you can type something in that's a base besides 10 or e. And that'll work on any calculator. Some calculators might have a function built into them to do this directly, but not every calculator does. So I'm showing you a method that you could even use this method on like just a regular scientific calculator, like a little $10 calculator you could type it in on. Some of the graphing ones have another way to do it as well.
For the 1084, at least the one that I have, you can hit the alpha key and then like the y equals for the graphing solve, and then you can go to the functions and it has a log base.
Yep. So some of the calculators have a function built into them that you can type it in. If you don't, you can always type it in this way and it'll work. Yeah, that's it. So let's try another example. So this one is going to be log base 3 of x. I want to graph that. Well, I can't directly because it's a base 3. But what I can do is I can rewrite it so that I can type it in. So can anyone tell me how I would rewrite this as a fraction using the change of base formula from above? Shai?
Log base 10 x over log base 10 3.
Yep, exactly. So that's what I'm going to put in y1. Okay. Log x divided by log 3. She could have said ln x divided by ln 3, and that would have been the same thing. All right. So let's type it in. Log x divided by log 3. I'm going to do zoom 6. To see what it looks like. Now you got to be careful because sometimes the graphing calculator doesn't draw things correctly. This is an example. That picture's not right. It's because when things get very steep on the calculator, it doesn't know what to do. So it's having a little trouble. Where does it look like, if I make that a little bigger, where does it look like the graph is starting on the y-axis? It looks like it's at -2, but watch what happens if I zoom in. I'm going to zoom in near -2, Does it still look like -2? No, now it looks like -3. That's like, what? What just happened? Well, it goes down forever. Okay? That's just something you have to remember. Log functions go like this. And it gets very, very close. Very close to the y-axis. And what do we call that if it gets close to it, but it never actually reaches it?
Asymptote.
It's an asymptote. So it's going to look like that. And that's going to go like that. Right? That's what it should look like. So, now let's answer the question. The domain. Okay? Domain is left and right. Does the graph in blue that I just put on the other page, does it go left and right forever? What do you think? How? No? Maybe? Katie? No?
Because it goes to the right forever, but it doesn't go to the left.
I agree. It does go to the right forever. It's just going to keep going. But when it starts going left, it's like it runs into a wall at the y-axis. It hits that y-axis and it's done. It doesn't keep going. So for the domain, does it ever reach the y-axis? We just said it was an asymptote. No. So it never reaches the axis. What number is the axis at? Jake? 0. So it never reaches 0, but it does go to the right forever. Okay. And now the range. Range is up and down. Okay. Does the graph go down forever? Yeah. Does it go up forever? Katie, what do you think?
Yeah.
It does. It doesn't go up fast, but if I were to keep drawing it, it's going to look something like that. It's going to keep going up very, 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 very slowly. In fact, it's basically going to look like it almost gets flat, but it never does. If you go to your table, type in a big number for x, like 25, you're at 3. Go to 500, you're at 5.6, still going up. Go like 9,000, you're at 8.2. So you can see how slow, right? From 500 to 9,000, I went 8,500 units on the x-axis, and the y-axis only went up, didn't even go up 3. So it's going up very, very, very slow. All right? So range is -infinity to infinity. And you can never change that. If a graph goes from -infinity to infinity, and you shift it up a little bit, it still goes up and down forever. Right? You could change the domain, but you can't change the range. Okay. Any questions on that? Okay. And when they say a complete graph, someone had a question about that in the homework. Sometimes they word that as find a viewing rectangle that makes it look good. I would say the viewing rectangle I have right here is well, the original one, is as good as you're going to get. That's fine. Now, you might be able to, if you go to second format, and you turn detect asymptotes off, I want to see if it actually draws it correctly. No, still doesn't. So there is no way I can make the calculator draw this correctly. All right, any questions on that one? Because just be careful on the test. When you're graphing a square root function or a radical, square root kind of looks like that. Let me graph a square root in red so you can see it. So there's a log, and here's a square root. You might think, oh, they look the same. Kind of, but not. I mean, they both have a curve to them, but remember, the log function has a vertical asymptote. For the graph in red, the calculator drew it perfect. That's exactly how it should look. It starts at a certain point, and it curves in one direction forever. So that's roots. Okay? Log functions always have vertical asymptotes. So they look kind of similar, but that's because the calculator can't draw the one in blue correctly. Yeah?
Apparently these calculators do have log base, but they're crossed out, and whenever you try to use it, it tends to save.
you're looking at them.
Well, you had mentioned that like you're not sure if these calculators have them, and you're gonna.
Oh no, I'm sure they have them. Yeah, I'm pretty sure. Ah. So yeah, when you use the change of base formula, just stick with that formula so that way it works on any calculator, even ones that have the log function mysteriously disabled for whatever reason. That's weird. I'll have to look at that. So, transformations. All the standard transformations apply to log functions. Doesn't matter. Again, we can go through it again, but I'm just going to say the same thing I've always said. Inside stuff is horizontal. Outside stuff is vertical. Any adding is a shift. Any multiplying is a stretch. Horizontal stuff is always the opposite of what you would expect. All right. So let's start with A. What would A do? It's inside and it's addition. So what kind of transformation would that be? I agree it's a shift because it's adding, but it's inside, so it's horizontal. I don't know if it's left or right. It depends if A is positive or negative. Right? But that's your horizontal shift. All right. How about B? We're still inside, but now it's multiplication.
Horizontal stretch.
That's a horizontal stretch. Again, I don't know if it would actually stretch or compress. Depends on if B is a number bigger than 1 or a fraction. Bigger numbers actually make it smaller. Smaller numbers make it bigger. It's the opposite. How about C? It's multiplication, but now you are outside the log function. What else besides here? Yeah. That's a vertical stretch. And that is exactly what you would expect. Bigger numbers stretch it bigger, fractions make it compressed, or they make it smaller. And Rebecca, how about D?
Vertical shift.
Yep, it's outside, makes it vertical. It's addition, makes it a shift. I don't know if it's up or down. It depends if it's positive or negative. Positive up, negative down. So it's a vertical shift. What if B or C was a negative in front? Well, what does that do when you put a negative in there? Yep.
Does it flip it?
It flips it. If you put a negative in front of B, B is a horizontal. It's a horizontal flip. If you put a negative in front of C, C is with the vertical. It would be a vertical flip. Okay? Some people say reflection instead of flip. It's the same thing. All right, so what I want to do is just explain how I could get this function starting with this function. Whenever you compare two functions, they always have to be the same base. Okay, I'm never going to switch the base part, but I might put negatives or any of the A, B, C, D that you see. And the reason I use the letters A, B, C, D is because that's the order you do them in. So it's A, B, C, D, in an order. Okay, so let's just let's start with the transformations. To go from this to that, how many transformations are there?
One.
Just one. There's only one thing that's happening. So I'll start by writing transformations for log base 3 of x to log base 3 negative x. So these are the transformations to get from the first to the second. Well, all you really have here is like a -1 where b is. So there's no stretch horizontally because it's like a -1. If you want to put the 1 in, you can. But what is the negative going to do? Connor?
They're gonna flip it.
Flip it? Which way?
That'd be horizontal. Right?
That's a horizontal flip, or you could say reflection. And Again, if you flip something horizontally, it means it does this. That's a horizontal flip from left to right. So it flipped over the y-axis. You could also say it that way. But that's fine. So we got a horizontal reflection. Now, find the domain, range, and vertical asymptotes. Okay, let's start with the domain. Well, we just graphed the log problem before. Let's graph another log. This time I'm just going to graph log of x. And is that how the graph should look? That's what the calculator told me. Must be right. No, it's not how the graph should look. What's wrong with that? It goes down forever, right? It goes down forever. So that's how it should look. Now, all we did was reflect that. We mirror imaged it over the y-axis. So pretend like the y-axis, you're folding it, and now it's going to go the other way. Would that change the range? That's the up and the down. If you mirror image it, flip it, would it still go up forever? And would it still go down forever? Emily? Yep, it still is going to go up and down forever. It's going to look more like this. Kind of. All right, so range, negative infinity to infinity. How about the domain? Would that change? Yep.
0, infinity.
Well, that's the original. It starts at 0 and it heads to the right forever.
Okay, sure. Let's go to the left and do 0, negative infinity.
Yeah, just we'll always put the smaller number first. So negative infinity up to 0. So interval is always written smaller number, comma, bigger number. I know negative infinity is not a number, but think of it as smaller than 0. All right, so there's your domain. How about your vertical asymptote? Did it move at all? Yep. No. The vertical asymptote was right here. Well, if you mirror image something, whatever was on the line that you folded the piece of paper on, it stays exactly where it was. The vertical asymptote was right on the line that we folded it on, so it doesn't move at all. So vertical asymptote is x equals 0. I almost wrote y equals. Y equals is horizontal. This is not, it's vertical. And that's it. Okay. Any questions on that one? So, I mean, the transformation could be a little harder than that because this only had one thing. On the test, you might see something with 2 things in it, like maybe A and C or A and B, but you might have 2 things rather than 1. Any questions on that? Okay. All right, actually, this is good. This has 2 things. Let's look at this one. You don't need to give me the domain and range here, just the transformations. Now, this argument, it's not written the normal way we write things. How can we write 3 minus x so that it looks more like this argument? 3 minus x, it's not the right order. It's not how we should normally write it. Emily?
Negative x plus 3.
Negative x plus 3. You don't have to do that, but that's just what I would do. Now, how many transformations are happening there? Alec?
2.
2, yep, there's 2 transformations. What number are we going to focus on first? It's going to be my first transformation. 3, I'm going to focus on that, plus 3. What is the plus 3 going to do? Okay?
Horizontal shift.
Yep, it's going to be a horizontal shift, and it's a plus 3. So which way is that going to go?
Up.
Let's stick with horizontal. I like horizontal, but just remember horizontal, up is not a choice for horizontal. We had that discussion yesterday in extra help. Yes. Plus is going to go the opposite way that you would think, so left, yes. So shift left 3. And what about log? So the second thing we already did in the last problem. What's the second thing that's going to happen? Yep.
Horizontal reflection.
It's a horizontal reflection. Yeah. Okay, so shift left 3, horizontal reflection. And that's it. Questions on that one? All right, so 2 things we have left. We're going to look at a couple graphs, and then we're going to look at a word problem. All right, so when we're graphing log functions, it's helpful to try to find the intercepts and especially the vertical asymptote. That's probably the most important thing to find. Every log function has a vertical asymptote. Once you find that, and you draw it, then you know your log function is either going to bend away from it to the right or away from it to the left. Okay? But you got to put that in first. As far as intercepts, your log function will always cross the x-axis. Always. How come? Why is a log function guaranteed to always cross the x-axis somewhere? Yeah? It goes up and down forever. So if something goes up and down forever and it's continuous, you never lift your pencil, it's going to cross the axis somewhere. But this one may not exist. Your graph might not cross the y-axis, like in this problem, right here. If you look at that graph in blue, it gets very, very close, but it never crosses the y-axis. So you don't always have a y-intercept, but you do always have an x-intercept. Okay. So, vertical asymptote, normally if you don't do anything, is right on the y-axis. What happens if you shift it? Well, it can shift. Right? Shifting it up and down doesn't really matter. Because think if something's vertical and you shift it up, it doesn't matter. If it goes up and down forever and shift it up, it still stays at the same spot. So the only thing we have to focus on for the vertical asymptote is the argument. Okay? Shifting left and right, horizontal stuff. Okay? That's the argument. Inside is the horizontal. So to figure out where the asymptote moves, just set the argument equal to 0 and solve it. Right, so your argument, remember, is like this stuff right there. It's the stuff inside the function. So set that equal to 0, solve it, and that'll tell you where your new vertical asymptote is. If you want to try to find the intercepts, remember the x-intercept is when y is 0. The y-intercept is when x is 0. So you just plug in 0. Which letter you plug in 0 for will control whether or not you're finding the x-intercept or the y-intercept. You can also use a table. Okay, we can use the table on the calculator, and that'll help us get some points too. But what you want to remember is log functions only curve in one direction. They never go in both directions at the same time. So you have to pick x's that make your argument positive. So if you had something like this, we're not doing square roots, log. Picking an x value here of -10, not a good choice. 2 times -10 is -20. -20 plus 3 is -17. That's no good. Okay, you picked one that was too small. Okay, you're going to get an error. Can't take the log of a negative number. So 0 would be okay. -1 would be okay. 2 times -1 is -2. Plus 3 is +1. But you can't go too much smaller than -2. You can go, or -1. You can go a little smaller, but you can never have this be a negative number. or even 0. It's got to stay positive. So make sure your argument is positive. And once you pick a value to plug in for x, like let's say I want to let x equal 5, I just plug it in, use my calculator, and then I can get y. And that would be another point on the graph. I would say for these graphs, you're probably going to need about 3 points. Maybe 4. Depends. 3 or 4 points. Okay, so let's try to sketch a graph of the one I have below. So it's log base 2 of 3x plus 5. All right, so first thing I'm going to do is I'm going to find the asymptote. How do I find the asymptote? What's the equation that I set up? Yep.
Set the argument to 0.
Set the argument to 0. Solve that, and that's the answer for your asymptote. So 3x equals negative 5, x equals negative 5/3. There's your vertical asymptote. Questions on that? Okay, so negative 5/3 is a decimal. That's like negative 1 2/3. So that's about negative 1.7. So when I graph it on paper, I'm going to try to put it at around negative 1.7. All right, so let's put that. Any question on how I figured out that that was around negative 1.7? Negative 5 divided by 3? Okay. All right, so negative 1.7, probably about, maybe about right there. All right, so next thing I want to do is I'm going to put that in the calculator, and then I'm going to try to find some other points in the table. Now remember, it's base 2, so can I type in base 2 with a single 0 button for it? Nate?
Not with not a single button.
No. So I'm going to type it in using the change of base formula. So log 3x plus 5 divided by log 2. Okay, I'm going to check, and I'm just going to make sure that that's the vertical asymptote. So if I type in negative 5/3, I should get an error. Yep, and I do. And now I just have to decide whether I should pick numbers bigger or smaller. What kind of x's do I have to pick to make sure that comes out positive? X's that are bigger or smaller? Oh, Sam? Well, somebody give me a number that's smaller than negative 5/3. Well, Morgan, give me a number that's smaller than negative 5/3. Any number you want, doesn't matter.
1/2 is that?
Well, 1/2 is bigger. So negative 5/3, that's about negative 1.7. So I need something smaller than negative 1.7. Yeah, let's keep it simple. Just negative 2, right? Makes the arithmetic easier to do. If I plug in negative 2, Emily, what's 3 times negative 2?
-6.
And then negative 6 plus 5?
-1.
Negative 1. Can I take the log of negative 1? No. So we went the wrong way. You can't pick numbers that are smaller. We have to pick numbers that are bigger than negative 5/3. Try it on the calculator. It doesn't work. Okay. So let's just pick a couple points. Let's do 0. We'll do 2, 8, and 10. So I'm going to graph those 4 points. And that should give me a pretty good idea of what this looks like. So 0, we're at about 2.3. About right there. 2, I'm at about 3.5. So 2, it's about 3.5. 8, a little less than 5. So 8, 5, be about right there. And 10, just a little above 5. A little bit above. Okay, and what's going to happen is my graph gets close to the asymptote. Which way is it going to go? Down. So I'm going to sketch it like this. So curves, tries to keep heading left. Think of that dotted line. It's like a wall. Can't go past it. And then it curves down, getting closer and closer. Okay, and that's it. That's your sketch. Question on that? All right. So it's said to find the domain, range, and asymptotes. Well, there's your vertical asymptote. We already found it. We had to do the graph. Domain. Michael, what's my domain here? What's my domain? Well, it's from the asymptote, which it's around negative 1.7. So negative 5/3 to infinity. Does it ever reach negative 5/3? No. No. So your domain is negative 5/3 up to infinity. And the range is the same for every log function that we study, no matter what. What's my range? Yep.
Negative infinity, comma 3.
It's always negative infinity to infinity. They all go down forever, they all go up forever. Okay. So it's important for the test to remember that the basic log function always curves up and to the right. The only way it wouldn't curve up and to the right is if you put a negative and you flip it. I mean, you don't even really have to remember that. You could just type log on your calculator and look at it and see, oh, the basic one goes up and to the right. If it did something like this, you've put a negative somewhere. You flipped it. Okay? So just keep that in mind. It always curves up to the right unless you put a negative and flip it. All right. Okay, so last thing we're going to look at is a word problem. And this has to do with the intensity of an earthquake measured on the Richter scale. So if you watch the news and you hear them say, a magnitude 4.6 earthquake or something like that, that's the formula that they use to get the earthquake. A, T, and B are all different factors that measure the earthquake and where it happened. So R is the magnitude. A is the amplitude of the vertical ground motion in micrometers. So that's something they measure when an earthquake happens. Okay, B is the period of the wave in seconds. And what that means is, if you think of easiest way to imagine it is if you throw a rock into a pond, right? You get waves that come out from where the rock hit. Well, that's just like an earthquake. You don't see the waves because it's in the ground. But if you had loose enough soil, you might actually see the wave coming at you from an earthquake. It depends. And B is a factor that accounts for the weakening of the wave. All right? Think about if an earthquake happened and everything was very hard and compacted, right? Energy transfers very easily. Okay, imagine putting your face up against a piece of wood in a door, and somebody hit the wood from the other side. You'd definitely feel that because it's very hard. It would transfer the energy. But put pillows on each side of the door, and then those are looser. They kind of absorb that energy. So it's like dropping a ball into sand, right? It just kind of absorbs all the energy. So B is a factor that accounts for probably what I just explained, how quickly the wave weakens. Right. So let's look at an example. Okay, any question on the formula? Okay. All right. So let's try this one. All right. So during an earthquake, the following measurements were taken. Following measurements were taken. All right, so let's make up some numbers, but I'm going to try to find something that is somewhat realistic, kind of works out. So let's say that the period of the wave, which letter is the period again of the wave? T. So let's say the period of the wave is 3 seconds. Bless you.
Thank you.
If you're wondering, what does that really mean? Well, if you imagine a wave like this, and the wave, maybe it was in water, and you were standing here watching the wave, it means that you would see the height of a wave, and then if you kept watching it, you would see another height of a wave 3 seconds later. That's how far apart the wave heights are in time. So period of the wave is 3 seconds. What letter is the factor that accounts for the weakening of the wave? B. So again, that's just some factor, maybe it has to do with the soil type. Let's say B is about 3.7. And the last thing we need is the measurement of the vertical ground motion in micrometers. And let's say the ground was moving 400 micrometers. Okay. Find the intensity of this earthquake. Okay, so intensity equals, what's the first thing that I put down? Log, yep, it's a log function. Okay, and what that means, because it's a log function, is anyone familiar with like pH scale in chemistry? Well, when you compare a magnitude 3 earthquake to a magnitude 4, it's not like you're just saying, oh, it's only one number higher. No, magnitude 4 is 10 times as powerful as a magnitude 3. So if you compare like a magnitude 5 to a magnitude 3, it's 100 times more powerful. Every time it goes up one number, it's a factor of 10 times as powerful. So it's kind of a big difference. So log, then we have a fraction. Okay, what goes on top? A, it's the vertical ground motion, divided by what goes on the bottom? T, period of the wave. And then what do we add onto the end? B, plus 3.7. Okay, so let's see what magnitude earthquake this would be. So we got log of 400 divided by 3 gives me 2.12 plus 3.7. So it's a magnitude 5.8 earthquake. That's a lot stronger than any real earthquakes we get around here, but I think some of the more powerful ones have been magnitude 7 or 8, which would, again, magnitude 8 would be over 100 times more powerful than this one. Well, that's it. Any questions on that? All right, so homework, you've already done the circle part. That's the homework for tonight. Let me just double check. Yeah, that should be fine. It's about 10 questions or so. Maybe 11. Okay, so we'll take a look at that. Tomorrow, probably have time to answer maybe a question or two, because then we're going to start the test because it's we only have an hour. Okay, so you've got just under 50, well, you've got a little over 15 minutes. So if you want to look at it and you have questions, now would be a good time because I'm not after school today. So if there's anything you want to ask me about the test now, just let me know.